Hello. In this presentation, we want to talk a little bit about what happens when you do an electrophilic substitution on a benzene ring that already has a group attached to it. In the previous two videos, I talked about electrophilic aromatic substitution on benzene rings as if there's just a hydrogen there and it replaces a hydrogen. But what if there's a group already on the benzene ring with some other hydrogens and you want to attach a further group to it? For example, what if we started with toluene with a methyl group already there, and of course 5 other hydrogens on those 5 positions, 1 on each of those 5 positions. And let's say we want to do a nitration on it. So we react it with nitric acid in the presence of sulfuric acid. What happens? There's 2 things we need to consider. One is, would it react faster or slower with toluene than it would with benzene itself? In other words, is this an activating or deactivating group? Activating or deactivating. Activating or deactivating. Does it make the reaction happen faster than it would if the methyl group weren't there, or slower than it would if the methyl group weren't there? And then the other question we have to ask ourselves is, where on the benzene ring is the new group going to attach? Well, it turns out that when we do nitration on toluene, we end up with a reaction that's faster than it is with benzene itself. So in fact, it's an activating group. And we get some of the new nitro group going on ortho to the methyl group, but more of the new nitro group going on para. So we end up with mostly para-nitro-toluene and a little bit of ortho-nitro-toluene, but no meta-nitro-toluene. So therefore, the methyl group, and for that matter, any R group, whether it's methyl, ethyl, propyl, pentyl, cyclobutyl, or whatever, is always what's called an ortho-para director. It's always going to go on ortho and para, mostly para. And by the way, if it's an ortho-para director, the reason you get mostly para rather than mostly ortho is because steric hindrance is just a little bit crowded there. So you get mostly para if you have an ortho-para director. So that's a methyl group. So we'll have to memorize somehow that any kind of alkyl group is always activating and always an ortho-para director. Let me give you another example. And by the way, that would be true if we're doing nitration. It would also be true if we're doing sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, or halogenation. It's still activating and it's still an ortho-para director. So it doesn't matter what the reaction is, it matters what the group that's already on the benzene ring is. Okay? So let's do another example. Let's start with benzoic acid. You know what benzoic acid is. It's a benzene ring with a carboxylic acid group on it now. And let's react that with nitric acid and sulfuric acid, just to be consistent. But again, you could do nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, or halogenation, and the same results would apply. First of all, does it happen faster or slower than it would with benzene itself? Well, it turns out in this case it's slower, which means that the carboxylic acid group is a deactivator, which means slower than benzene. Excuse me. And it turns out that the new nitro group ends up going on meta. Very interesting. In the case of a methyl group already on the benzene ring, we saw that it went on ortho and para. In this case, it ends up going on meta. So therefore, the benzoic acid group must be what's called a meta director. Okay. So we'll have to memorize that as well. It's going to turn out that all groups that you might find on a benzene ring will either be activating and deactivating. I should say, will either be activating or deactivating, and they will always be either meta directors or ortho-para directors. So if it's going to direct meta, it's just going to direct meta. If it's going to direct ortho, it's also going to direct para, and vice versa. So it's either meta or it's ortho-para. Is it true that all deactivators are also meta directors? It is true for the most part, but there's one exception, which I'll show you right now. So let's do a third example. Let's start with chlorobenzene. And let's do nitration. And again, I'm using nitration in all of these examples just to be consistent, but keep in mind that the same results would turn out if you did nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, or halogenation. You would still get the same results I'm going to talk about here. First of all, is the chlorine group activating or deactivating? It turns out it's a little bit deactivating, slows the reaction down. And the product that you get of this particular reaction is, what do you think? Some ortho and mostly para. Oops, excuse me. Mostly para, so you get both ortho and para, but mostly para. So therefore, a halogen, and this is true whether it's chlorine, bromine, iodine, or fluorine that's on the benzene ring, any of those four halogens are always going to be deactivating, and they're always going to be ortho-para directing. Okay. So, essentially what you have to do is memorize for each of the different groups that you might find attached to a benzene ring, is it an activator or a deactivator? And secondly, is it an ortho-para director or a meta-director? Fortunately, there's some generalizations we can make, and I will refer you to the table in your textbook on page 852. And I will summarize basically what it says at this point. It lists in that table 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 26 different groups. From nitro groups, chlorines, bromines, iodines, benzene rings, alkyl groups, amino groups, OHs, ORs, carboxylic acids, ketones, bunches of groups that you can print on there. And it gives for each one of them whether it's an ortho-para director or in a meta-director, and then whether it's activating or deactivating. I'm going to summarize it in a little bit briefer form, although I do recommend that you look at that table and essentially memorize that table. But there's some generalizations we can make here. So first of all, let's list all of the groups that are both activating and ortho-para directing. And that's going to be most of them. Most of the groups are activating and ortho-para directing. Those are going to be things like alkyl groups, so methyl, ethyl, propyl, isopropyl, N-butyl, isobutyl, T-butyl, sec-butyl, various pentyl groups, cyclopentyl groups, cyclohexyl groups. Any kind of alkyl group is going to be activating and ortho-para directing. Also, any kind of benzene ring will be. So if you have a benzene ring already on a benzene ring, it will direct ortho and para, and it will be activating. Right? So those two kind of stand alone. Those are carbon groups. And then we also have anything with a lone pair, and that includes oxygen with lone pairs, whether it's a hydrogen or an OR group. So if it's methoxy or ethoxy, or if it's just an OH group on a benzene ring, so in other words a phenol, then those are ortho-para directing. And for that matter, anything with a nitrogen and a lone pair. With these two groups could be hydrogens, could be one hydrogen and one carbon group, or could be both carbon groups, the same or different from each other. Could even be a C double bond O on one of these. So it could be an amide group as long as it's the nitrogen that's directly attached to the benzene ring. So in each of these cases, remember, this is the benzene ring on which we're going to try to do the electrophilic substitution. Okay. In this case, obviously, it's got two benzene rings because we're doing electrophilic substitution on this one, but it has another benzene ring on it. And then same thing here, this would have a benzene ring on it. So anything with a benzene ring, a carbon group, or a group with a lone pair, either oxygen or nitrogen, fits into this category. Okay, so let me quiz you based on this category. What would you expect to get if you reacted, let's say, biphenyl with, let's say, SO3 and H2SO4. And let's just do one equivalent. Okay, so I'll let you turn off the video here for a second and see if you can write the product of that reaction happening once. Welcome back. Let's go ahead and do it. We are going to substitute onto either of the two benzene rings, doesn't matter which one since they're the same as each other. Let's just choose to do it on that benzene ring. Let's remember that the other benzene ring is an ortho-para director, and when you have ortho-para directors, you get mostly para. So we're going to go para to that original benzene ring. And our product would be that compound. Is that what you wrote down? Well, it should, because again, the second benzene ring is an ortho-para director, so you get mostly para. Let's do one other example. What would you expect to get if you started with anisole? Remember, anisole is methoxybenzene, it's a special name. And instead of doing sulfonation, just for fun, let's do halogenation. So let's do Cl2 and FeCl3. What would you expect to get? Again, stop the video for a second, write down your product, and then rejoin me and I will draw up here on the board. Welcome back. Because the methoxy group is an ortho-para director, we're going to get the new chlorine going on. Para, mostly. You get a little bit of ortho, but mostly para to the methoxy group. Okay, so those are the ortho-para directing and activating groups. Now what we'll do is another group which has lots of members in it, but it's a completely different thing. These are going to be deactivators and meta-directors, and it turns out that almost all the deactivators are also meta-directors, the vast majority of them. So what are they? Well, we've already seen a carboxylic acid group. Carboxylic acid group, where the carboxylic acid is directly attached to the benzene ring, will act as a meta-director on the benzene ring. But also anything with a C double bond O there. So esters, ketones, aldehydes, anything where you have a double bond O directly attached to, or where you have a C double bond O directly attached to a benzene ring, those are always going to be meta-directors. Similarly, S double bond O, OH. So sulfonic acid groups, again, has a double bond O right next to the benzene ring. Those are going to be meta-directors and deactivators. Also cyanide, which is another one of the derivatives of carboxylic acids, if you remember back to that chapter. And it's for the same reason. These are all electron withdrawing groups. They're all groups that are pulling electrons away from the atom directly attached, and therefore pulling electrons away from the benzene ring, and we will see why that matters when we do the mechanisms, and when we talk further about the mechanism in the next video. What else? Well, if you look at the table on page 852, you will see also that we have strongly deactivating nitro groups. And of course, you remember that that's actually an N double bond O, single bond O with a positive charge. So again, there's that double bond O, just like in all the rest of these except for that. And of course, that's a triple bond N. But also, and here's some weird ones, an NH3 group with a positive charge. So that has a full-fledged positive charge next to the benzene ring. Again, electron withdrawing makes it a deactivator and a meta-director, CF3. Now that may seem weird because you say, well, that's an alkyl group, and we already saw that alkyl groups are ortho-para directors, but this is a trifluorocarbon, and fluorine, being very electronegative, pulls electrons away from the carbon, which then pulls electrons away from the benzene ring. So again, it's a electron withdrawing group, as are all of these, and therefore it's a meta-director and a deactivator. And similarly, CL3, same idea, not quite so strong, but it also, the three chlorines, pulls electrons away from the carbon, which then pull electrons away from the benzene ring and makes it a deactivator. So those are the meta-directors, deactivators. And then there's yet a third category. Oh, let me quiz you before we go into the third category. what if you had, let's say, how about an amide? Notice it has a nitrogen with a pair of electrons. So you might say, well, that's an ortho-para director because it has a pair of electrons. But notice that the pair of electrons is not right next to the benzene ring. Instead, we have a C double bond O right next to the benzene ring. That makes it a deactivator, meta-director. And if we did, let's say, a halogenation on this, the Cl2 and FeCl3, where would the chlorine end up going? Meta to the original group. And that's because the C double bond O carbonyl group is an electron-electron group. It's a meta-director. It's a deactivator. So you get it going on in the meta direction. Okay, let's look at the third category. The third category is pretty short. Only has 4 groups in it, and really they're all the same as each other because it's just the halogens. These are deactivators, but ortho-para directors. So let's keep in mind that most deactivators are meta-directors, most activators are ortho-para directors, the halogens are deactivators, but they're ortho-para directors. So you just have to keep that one exception in mind, and that includes chlorine, bromine, fluorine, and iodine. So let's do an example. If you had a bromine on the benzene ring, and you did a chlorination, Cl2, FeCl3, what would be your major product? It's an ortho-para director, so we'll get mostly para. So we'll get that as a major product. That finishes our discussion of the various groups that will act in different ways that are already on benzene rings. But before we finish the video, I want to ask you to consider what if we had 2 groups already on the benzene ring and we were trying to decide where would a third group attach if we did an electrophilic substitution. So let's just do some examples. I think that's the best way to explain it. How about if we started with a group that had 2 meta-directors already on the benzene ring. Could be 2 nitro groups, could be 2 cyanide groups, could be 2 carboxylic acids, or some combination of any of these meta-directors, and I happen to have a carboxylic acid and a nitro group here. And let's say we wanted to do an electrophilic substitution, like let's say chlorination. So Cl2, FeCl3. Where will the new group go? Well, let's consider each of these 2 in turn. The carboxylic acid would direct a meta to itself, which would be this group, and this one over here. But this one over here is already blocked, so obviously we can't replace the nitro group. We can only replace hydrogens. The nitro group will direct meta to itself, which would be this position and also this position. But again, that group is blocked, so the only one it can direct to is there. And since both the carboxylic acid and the nitro group are directing to the same position, we will get essentially 100% of that. So that's a case where both groups are directing to the same position. There's really no confusion about that. But what if we had 2 meta-directors not in meta positions? But let's say we had a carboxylic acid group and a nitro group, this time para to each other to start with. One thing you might wonder is, well, how could you make that since they're both meta-directors? How can they end up being on para? Well, believe me, there are ways of doing it, although it's not directly. You have to do a little bit longer synthesis. But let's say we started with this compound, and let's try to chlorinate that and see what happens. Where will the new group go? Well, this meta-director is going to direct to this position, which is meta to it, and this position, which is meta to it. And the nitro group is going to direct to this position and this position. So essentially they're fighting each other. Which one wins? Well, in this case, they're both about the same, so you're going to end up with 2 possible products. which would be that one, which of course would be called 2-chloro-4-nitrobenzoic acid. And you'll also end up with a fair amount of the chlorine going in that position. And of course that would be 3-chloro-4-nitrobenzoic acid. And you get both in this case. So in a case where two groups are on the ring and they're fighting each other in terms of where the new group should go, at least as long as they're both meta-directors, then you get both products. What if we have two orthopara directors? Let's say the two orthopara directors are already on, let's say a methyl group and a, well, let's put a bromine on there. Okay, we know that bromine is an orthopara director and a methyl group is an orthopara director. What do you think? Well, this one's going to direct to its ortho positions and para, but para is blocked, so it can't go on there. This one's going to direct to its ortho positions and para, but its para position is blocked. So really, it could go on these two, or go on either one of these two, or either one of those two. Which one wins in this case? Well, it's going to turn out that when you have an activating group and a deactivating group, doesn't matter whether they're orthopara or meta-directors, the activating group is always going to win. So the methyl group wins out over the bromine because it's activating and the bromine is deactivating, and we will get then mostly the new group going on ortho to the methyl group in that case. If this was chlorination, for example, the new chlorine would go there. So we'd end up with 2-chloro-4-bromo, I guess you'd say 4-bromo-2-chloro toluene in that case if we were chlorinating. So the fact is you have to look at each case separately. You have to analyze where is each group going to direct the next group to, and if there's more than one group, look at them in terms of being in competition with each other, and the one that wins will be the one that's more activating. If they're both deactivating, then you just have to consider that you may get more than one possible product in any particular case. That will end the presentation. Thank you.